a pleasure and an honor to be speaking here at JACFest. So many of the books that were cited for the proof of that wonderful theorem yesterday were texts that were fundamental in mathematical education, and many of the notions introduced and discussed in those texts actually can figure in here. So, okay, so just to review the setting here. So, we're studying rational maths from P1 to P1, projective space, one dimension. With the parameter space, it's a smooth affine algebraic variety of dimension 2D plus 1. Okay, and there's an automorphism group of P1, calling it odd here. It's also known as Mobius transformations, or RAT1. It's a group that acts on RAT-D by conjugation. There's a quotient space. So the quotient space is itself an affine algebraic variety. It includes 3 dimensions. The quotient has dimension 2D minus 2. Okay, the quotient can have singularities. They're not so bad. I'm going to talk my way around the singularities when they come about. This lecture is not about that. Okay, I'm interested in various infinitesimal questions concerning such spaces and maps between them. This is just a sample. So we have this quotient projection. If you pretend that the quotient space is a manifold, or if you look away from singularities, or if you say something about transversality to orbits, you can ask whether this quotient projection is a submersion, meaning that the derivative is surjective. You can ask if iteration, so iteration takes you from a parameter space of lower degree maps to a parameter space of higher degree maps. Evidently, an algebraic morphism is, when does this induce an immersion? Okay, and then sort of more technical questions involving the behavior of various dynamical variants of cycles or critical orbit relations. You can have, you can consider cycles with specified period multiplier, and that will cut out, to oppose a condition like that, will cut out a locus in parameter space. Similarly for parabolic cycles, degeneracy and index with critical orbit relations. You get these loci. You can do several at a time. When are they smooth? When do they intersect transversely? Okay, so
Adam, 2 questions. So
yeah.
I've already forgotten what the difference is between big R and little r.
There's a quotient projection.
What's the difference between the spaces?
One is all rational maps. One is rational maps up to conjugacy.
Modulus.
Modulus.
So, and that's little r is modulus?
Little r is modulus space.
And when you say when does iteration induce an immersion, you don't, it's not a question about, it's more where does iteration
Where and when. These are evocative questions. When also means where.
I mean, if you ask for which D does it
all, you can further, no matter how much the question will be further refined beyond anything you'll ask, so it just please wait. Okay. So, under what circumstances can one, where circumstances means whatever it means. Okay, so in order to do this, we need to address certain basic issues, because if you start writing all this down, you can handle various cases and coordinates, but it starts to get very, very messy and daunting. So to actually make any progress, we need to describe the tangent and cotangent spaces of our parameter space in an intrinsic way. And I want to emphasize this is absolutely not merely a matter of pedantry or aesthetics. We're interested in results valid over fields. Okay, the talk says arithmetic. Okay, so when and where may, for example, also include what characteristic. Okay, so even though this is a Holomorphic Dynamics conference, and even though, of course, I'm secretly doing things over C because that's sort of what I really care about, I want to do things algebraically because actually what I want to prove over C, or what someday I'd like to prove over the algebraic closure of the rational numbers without reference to C. And one would imagine that much of that argumentation, if not all of it, and a lot of the formalism might actually make sense over characteristic P, and it's interesting to see how far one can go without having to commit oneself to a given characteristic. So to do this, we need to step back, and instead of working in the category of complex analytic manifolds, we need to do a little bit of algebraic geometry. So I just want to give a quick review of some formalism. This is just to get this up here. If you are not interested in characteristic P, or if you find this generality absurd, just ignore it and think C all the time. But you will notice I will never make reference to anything analytic about C, and I will not even make reference to real and imaginary parts. Okay, so basic fact now, there's up to isomorphism, there's a unique smallest algebraically closed field of given characteristic. We either have characteristic 0, and it's the field of algebraic numbers, or it's the closure of finite field of characteristic P. And it turns out that for various purposes, including all of our purposes, these are the only fields you need to consider. Okay, many properties of such fields, and all first-order properties, which is just some technical division, it's nothing, I won't bother saying it, what it means, but if you fix the degree, then essentially everything I'm saying here is first order. Okay, and this is sort of codified, so many people have heard of the so-called Lefschetz principle. It basically says there's just sort of one algebraic geometry in any given characteristic. In particular, the results that you would get for C, algebraic geometry over C versus over Q bar, are going to be the same statements. Whether or not you can prove them the same way. And it might even be that to prove a result for over Q bar, the only known way at the moment is to invoke this principle, move over to C, and do some complex analysis. For example, the proof of Thurston rigidity, which of course is my secret motivation in all of this. I would like to get around that. And I'll admit to you right now, I can't. It's not happening in this talk. But I'm setting up all the formalism there so that if someday somebody figures out how to do it, you just plug it into this and then go. Okay, so just some words. This is just so, in case anyone is bothered by what it might mean to consider a tangent vector to some algebraic variety defined over the closure of a finite field. There's a formalism for this. You can get it out of commutative algebra. This is what is set up in basic algebraic geometry classes. So I'm going to discuss things in the context of algebraic varieties, which is probably not optimal. If I were really, if I were professional rather than faking it, I would do schemes. But there's nothing I'm going to do here that requires schemes, and it would annoy people. So just varieties. And these will end up being smooth varieties, and you can forget all this in a minute and just go back to your preconception about parameter space of rational maps, except what I say would be legitimate over Q bar or FP bar. Okay, so for example, I will be talking about smoothness, tangent vectors, derivatives, and so on and so forth, but it's all okay. You can hook it up out of commutative algebra. And this last point here is this is more or less, this is one of the main things that distinguishes varieties from schemes, and it's anything about transversality is somehow a statement along these lines. So there's only trivial nilpotent elements. In other words, reduced versus non-reduced is the difference between looking at the zero locus of the equation of x equals 0 versus x squared equals 0. Okay, you might say, what's the difference? You can attach a difference because, of course, the second one has a multiplicity. I don't want multiplicities. Okay, so, all right, you have objects, you have morphisms. The morphisms are what you think they have, what you think they are, but to actually say everything, you can't just discuss things in terms of topology. These objects come equipped with so-called structure sheaves, which basically tell you what counts as a holomorphic function. And then the compatibility is given here. There's a definition of tangent vectors in terms of various types of ring endomorphisms. Duality gives you cotangent spaces. You get derivatives. So you can talk about all that. It all works the same way. You get the chain rule, all that good stuff. You don't quite get the inverse function theorem. You're not going to need it, but there are ways around that are more elaborate. It's just a comment. Okay, now this is the most acknowledgement I have here to arithmetic. If you actually mean to take this seriously and are doing the characteristic P stuff for real, then there is some further complexity that comes about here, because there's a notion of, ramification behaves in funny ways. So for example, you you can have a, you can just easily write down maps. Do I have one here? Maybe I don't. Oh, there it is. You're right, z goes to z to the p. What happens if you take the derivative of z goes to z to the p? Now, we all know how to take derivatives. The algebraic derivative is going to work the way you think it is. So the derivative is going to be p times z to the p minus 1. Okay, but of course, if we're in characteristic p, that comes out as 0, which means that for the point of view of taking derivatives, that map behaves as if it's the constant map, which of course it's not. Okay, so those maps are called inseparable, and they're a pain in the neck from the point of view of this formalism, so we'll just simply ignore them. Something which is also annoying, and not quite as annoying as inseparable, but still somewhat annoying, is wild ramification. So in general, there's a sort of unholy conspiracy that can happen between the characteristic of your field and, for example, local degrees or global degrees, and you basically you have to think much more carefully, and there are funny things that happen if the characteristic happens to divide any of these. Characteristic 0, it's not an issue. So again, if you're only interested in C or Q bar, forget about this. But just to show that I check things, certain statements I'm making are actually accounting for the exceptional behavior here. Okay, and the point is that if you restrict attention to the separable case, then, in other words, where you don't have derivative 0, then version of Riemann-Hurwitz applies. Things behave more or less as you'd expect. In particular, if you count critical points properly, which does not necessarily mean by the local degree, this is a wild ramification. But if you count your critical, record your ramification properly, you do get a ramification divisor of the correct degree. On the other hand, here's a wild case here. Again, if you just take derivatives now, here in characteristic P, the derivative of that comes out as 1, which means at least not if you're in affine space, you have no critical point. So the only place that you can have ramification is the point of infinity. Okay, that's a wild thing because over C you need to be ramified over at least 2 distinct points. So you have all the ramifications sitting over that one point. So this complicates the formalism somewhat, and I will often talk around wild cases because I haven't really figured out the right way to say it. All right. Sheaves are your friends. I know there's this allergy and irritation and so on and so forth. There's a learning curve with sheaves, but honestly, it might sound scary in the beginning, but it saves work much later on. Sheaves and cohomology are simplifying devices to avoid unnecessary excursions into coordinate-dependent computations, which cancel out to 0 anyway. So you just set it up right to begin with and you never do those computations. Okay, so the formalism of Shields was discussed in Hamill's talk. I'm just giving you some examples. I'm interested in types of objects. I'm interested in typically arise as sections of holomorphic line bundles. These might be holomorphic functions, holomorphic vector fields, holomorphic differentials, quadratic differentials. And then for every holomorphic version, there's a meromorphic version, because you can talk about meromorphic sections, what it means for a section, for an otherwise holomorphic section of such a bundle to have a pole somewhere and what the order is. Okay, so you can modify these. You can, for example, look at holomorphic vector fields, the bundle, the sheet that gives, and then modify and say, well, actually, I really want to be requiring zeros at certain points. In other words, being holomorphic but not 0 might sort of count as meromorphic, right? So there's a formalism for that's what this is about. Okay, and then every once in a while we'll talk about certain quotient sheaves. These are what are called skyscraper sheaves. They behave a little bit different. Essentially, this came up, Hamill asked a question in Gomez-Mont's talk. It's just part of the formalism that you can form exact sequences of sheaves, and you can get quotients, and you just have to compute them from the formalism.
So, Adam,
Yes.
since you're willing to work over more general fields, do you really need holomorphic, or do you just need to help?
I mean regular, but I put the word holomorphic in here so that people would feel comfortable.
But it's different.
Well, what do you mean different?
Well, the sheaf of holomorphic functions is not the same as the sheaf of algebraic.
Okay. So what I should say here is the sheaf of regular functions. I said meromorphic, holomorphic here so as to not confuse. Because some of them saying meromorphic anyway. There's regular and meromorphic, right? It's true. Holomorphic evokes the analytic category. perfunctorial characterization of cohomology. Cohomology is whatever does this, okay? And this property characterizes cohomology uniquely up to unique isomorphism. So I don't really, it just suffices to know that it can be computed. And if I ever do need to compute it, I'm going to compute it. I won't even show you the computations, but a fairly down-to-earth way to do it is a classical idea called repetitions or adels, where you essentially get at your higher cohomology by looking at singular parts of, for example, polar parts of your of local sections, and up to some equivalence. Okay, and I didn't want to spell out. And I didn't want to actually spell out what that is, because I'm not going to actually illustrate the computation, but this is not difficult. It's not my preferred, well, it's a cute definition. But this growing deep definition here is better. Okay, statement, this came up in Xavier's talk, where he used this formalism. So the tangent, what is the tangent space? Tangent space to a rat D, this is parameter space, now not moduli space. So it's canonically isomorphic to the space of global holomorphic sections of a certain line bundle, or the sheaf associated with the line bundle. That's F with the 5-pointed star of the tangent bundle. Now what is that? This is what I'll call a pullback bundle. The trouble is the word pullback gets used in two slightly different ways in this discussion. And the usual way we mean pullback, when we pull back differential forms or vectors and so on, is really what's given in the second line. And the point is that in the separable case, there's a canonical isomorphism that lets you go from the first presentation, which is always available, to the second presentation, which is somehow more congenial for what I want to do here. And we do it all the time. Okay, so this step happened in Xavier's talk, and I'm going to do it too, which means that once I start actually spelling out the formalism in detail, I'm going to be in the separable case at minimum, and probably in the tame case. And of course, secretly over at P-bar, because I'm really a complex analyst. Okay, and this is close to a proof of why Xavier gave some details about this too. It's just, how would you figure out what a tangent vector is in anything? You take a curve in that space, okay, and then you just somehow figure out from the definition, general definition of what a tangent vector should be, what that is. And here you can just follow individual points. Individual points give you tangent vectors, but they are not attached to the point you start with, they're attached at the image point. So if you just take the derivative, d by d lambda here, you don't actually get a vector field. Well, you'll get a field of tangent vectors, you get a field of vectors tangent at the image, and you can try to transfer them back using the inverse of the derivative, because that will take, the derivative will take tangent vectors at x and tangent vectors at f of x. So long as you can invert, you can bring them back where you want them. When will this go wrong? Well, when x has critical points, and then if you check, what you'll do is you'll acquire some poles whose order is, say, whose depth is bounded by the critical. Yes.
Could you tell us what theta sub r means?
Theta is the sheaf of holomorphic vector fields on P1. That's a gamma. That funny thing is a boldface gamma. Gamma sub f is the critical divisor of f. Okay, so let's just put aside all the pretense of finite fields and ramification. Okay, so look, if you're working over C here, a rational map has 2D minus 2 critical points, counting multiplicity. If there's no multiplicity, it's just 2D minus 2 points, full stop. So you could say gamma sub f is that set. But more generally, some of these points could have multiplicity, so it's really that divisor. It's a multi-set. Okay, so on an earlier slide, maybe, okay, so theta sub gamma sub that means, so H0 of that is the space of meromorphic vector fields, which are holomorphic away from the critical points, and such that the poles, for example, if the critical points are all simple, then you only allow simple poles. The worstness of the order of the polar order is less than or equal to the order of the corresponding critical point.
So this is theta twisted by the divisor here of that.
Okay, if that's the language.
Right?
Yeah. And the sign is right. I mean, there's one I always wonder if there should be a minus sign there, but this is the way it should be. So you are allowing poles. If I had a minus there, it would be sort of mandating zeros. Okay. is formalism. I mean, it's like a two-line computation if you actually want to do it, right? But composition, I mean, what you have maps, right? So where grad D is a space of maps. So if I compose, that should give me some map between parameter spaces, right? I mean, you could write down low degree cases by hand using Maple or something, so it certainly is an algebraic map, a regular map. And here's a statement about the derivative. There is a corresponding, I mean, of course, this is derived from a formula in the pullback level presentation where you don't need the separability assumption, but if you want to transfer things over to these twisted, they're called twisted bundles here, then you need separability for that. And this is just the chain rule. This is just what it works out to be. But notice how simple the formula is. Okay, I can apply this now. Corollary, first corollary. If I fix a map and then imagine conjugating it by Mobius transformation. In fact, I'm actually really only concerned with doing all this in a small neighborhood of the identity. Because remember I said I was going to talk my way out of automorphisms. This is how. When I perform my quotients, I'm really only interested in quotienting out by the small, by Mobius conjugation near the identity. And this allows me to pretend, if I ever need to, that my quotient spaces are actually manifolds. So if I ever write something down as having a cotangent space or a tangent space and you think I'm lying, that's what's happening. Okay, as an immediate corollary, one or two line computation from the previous, you get this. Okay, the derivative of the order of the identity is given by, so V, what is the H0 of theta? Another name for H0 of theta is little SL2 of the field. Those are just the globally regular vector fields. There's 3 dimensions worth of them, right? You can write them down, you know, the quadratic polynomials times d by dz. That's all that is there. And then you say the vector field, we know how to pull back vector fields. That's what's given in the previous formulas, right? Coordinates you compose with a pre-composed map, you divide by derivative. Okay, so that operation is pullback. So you have identity minus pullback, and this is the derivative. Very, very clean formula. Another formula, this was used in Xavier's talk. It wasn't quite written this way, but there was a formula that's a lot like that. Or perhaps a little of that. So the derivative iteration, again, the use of the separability hypothesis is just because I want things in the form with theta sub things rather than pullbacks. So it's just the sum of pullbacks by the iterates up to one less iterate. So V goes to V plus F pullback of V plus dot 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 plus F to the n minus 1 pullback of V. Okay. This is called a theorem here. This is actually no great shakes. It's just that I wanted to distinguish them from the corollaries. This is an easy thing. If I were neglecting all of this arithmetic nonsense, I could write the statement and the proof in 2 lines. But I wanted to just illustrate to you in one case what it means to pay the extra attention to finite characteristic in a case where I actually knew how to do it. Okay, so are there going to be pullback invariant global meromorphic vector fields? And the answer is basically no. Let's just say, first of all, if you're working in characteristic 0, let's say over C or Q bar, same thing, the answer is going to be no, and you could actually probably figure that out directly. I'll have the argument in the next page. It's a well-known fact. Stronger versions are used, for example, in proof of Thurston rigidity to say that the characterization of pullback invariant quadratic differentials, right, this is weaker than that. So if you prove that there's essentially no pullback invariant quadratic differentials up to appropriate scale, then it will apply this. If you could go from a vector field to a quadratic differential by doing, 1 over the tensor square, the dual of tensor square. Okay, so I've just sort of spelled it out here. I'm really only interested in showing that lambda is not 1, whenever I can show it. When and wherever and in whatever characteristic I might be able to show it. Okay, so these are the facts spelled out here. And I've got a couple examples illustrating some of the funny business in finite characteristic illustrating. For example, so in characteristic 0, you're safe, right? Because for example, if you have the map Z goes to Z squared, then you can pull So
What happens to like this examples?
it's not about that.
When there actually is R?
Well, yeah. That's not the one over. No, test examples for quadratic differentials. You see, the square root, that would have half integer order. But the corresponding thing would be powers and DC bar. If you take a lattice example, the quadratic differential involved is not coming from the square root vector field because you have simple poles. That's why the quadratic differential discussion contains the vector field discussion. It's sort of like, not necessarily oriented versus oriented. Anyway, I'm going to prove this in the next page. Because the proof comes immediately out of this lemma. Now, everybody knows this lemma, but probably the proof of this lemma that everybody knows uses the word Julius set or Montel's theorem. But fortunately, you don't need to do it. And I remember working this out myself many, many years ago. It's probably in Joe Silverman's book too. Fortunately, I was able to reconstruct it. Here's a proof, a completely valid proof.
Adam?
Yeah.
The usual proof just uses the Euler characters.
All right. Well, that's basically.
Not Julius then.
Well, what does usual mean?
What a normal person would do.
I agree, but as I was searching for things, all right, fine. I know.
I'm just saying there's a topological proof that is just finding Euler characters.
Yeah, well, fundamental theorem of algebra, covering, that's all the same. What I'm saying, I do not want the Montel's theorem proof. That's all I need. Your topological proof is no doubt the same as the algebraic proof. But anyway, here it is. And that two, of course, is your two and Euler characteristic. Xavier said I shouldn't show this slide. Don't read this slide. This slide is just to show that I actually checked something. I mean, it's essentially the argument that appears in various places to classify the pullback, the eigen quadratic differentials under pullback, except it's a little bit more involved because since you see, okay, that everything comes from that what's on top there. So the invariance part is just that equality again. Now, what's the inequality for? If you're working over characteristic 0, that's going to be inequality. You just work it out. How do you? What's the order of a 0 or pole of a pullback of a vector field? There's a formula, and that's the formula. It's just that in the case of wild ramification, right? The way the ramification divisor is not what you read off naively from the local degree. Why is that? I mean, I don't know if I had the example or not, because if you have like z to the p plus z to something else, okay, you'll see the p as your local degree. When you want to compute the ramification divisor, you're really looking at the vanishing order of the derivative, and that's going to involve the higher power that you see after the term that goes away. Okay, so that's why the inequality is there. So you have to fight against that inequality if you actually want to prove this. So there were 2 extra lines of discussion. But morally, it's because 0 and pole sets under the right assumptions are both going to be backward invariant because of this. Poles always and zeros in the tanh case, and they're finite obviously, and finite backward invariant set is only 2 points, and you can't have zeros there. That's excluded again by that relation. So that's the proof, and then you just work through this and see what plus or minus 1 over d might work out to be in various characteristics. Okay, so just now immediate corollaries of the formal statements I had that about what these derivatives are, and that invariant vector field characterization is this. So here's an answer when you're asking what does when mean where or in what characteristics. So it means a statement like that. And I'm not saying that this is sharp. I just wanted to sort of spell out reasonably digestible statements that, for example, only mention tameness or degree. Nothing is if and only if. So similarly, under such assumptions here, and with the correct interpretation of the tangent space, so to speak, of moduli space, this is when you can expect the quotient direction to be submerged, which, by the way, is always in characteristic 0, right? The issue doesn't even come up. Why is this? Because you see, the reason the issue doesn't come up in characteristic 0, I guess the statement would be locally, again, avoiding away from singularities in moduli space, you have it's a local product in the smooth category, right? The moduli space and the fiber. There's because this never vanishes, because you can't have this, but except you could have this in certain funny cases in positive characteristic, and you just deal with it. Okay, there's a similar discussion for immersions. It works out, the fine point, the fine print works out to be slightly different, but again, there's a basic statement that's true over characteristic 0, and then the way you have to modify it, because, you know, plus or minus d to the n might work out to be 1, because of the characteristic. Okay. Anyway, as a corollary of all this, now, here's the statement. I mean, there are proofs of this over C using Julia sets. For example, this is basically the statement that a map can only arise as an iterative of finally many other maps. Okay, and there's various proofs of this over C, and the one I seem to remember involves Julia sets, which was very transcendental. There are no doubt other proofs. I've never seen an algebraic proof, so I'm giving an algebraic proof here. Now, of course, if you're interested in characteristic P, so the above setting, if there's some fine print of excluded here, I have not thought about this long enough to wonder if there's actual violations of this. I don't think there are, but in any event, if you're just thinking over C, this is a way to prove that. So when we finally many maps of lower degree can iterate up to a given map. Okay, now here's where it starts. Once you start to approach the interesting questions about local dynamical invariance and what happens when you move, what happens to them as you move in parameter space, or with critical orbit relations, it starts to get a little bit hairy, and you either need some more formalism or to write formulas down local coordinates. So here I just want to give some ideas, give an idea of the sorts of things one can get out of that formalism with more or less minimal effort. Okay, so this statement here, this is actually not particularly hard to prove. This is an exercise in the formalism, a simple dimension count, and the residue theorem. I am not using Thurston's theorem in here. I am not using contraction. I'm not using anything. It's a simple form of calculation. Notice I say fixed points. Much, much more elementary than if I said periodic points. Notice I also do not say non-repelling. Okay, so there's a proof of this using basically playing around with things that you can formally, this lemma here, versions of this lemma, not these particular quantities, but some other, perhaps, but some other quantities came up in Xavier's talk, precisely in this formalism. And what's interesting here is what I found when I sat down to do this, a while ago, if I sat down to do this, I was really thinking of multipliers. And I just sort of figured, let's just ignore the cases where you have parabolics, let's just look at maps that have d plus 1 simple fixed points and record their multipliers, and let's show that those multipliers are give independent coordinates. Well, they're not quite going to give you independent coordinates, because you know there's at least one relation, the holomorphic index formula, which has come up in many of these talks, which Jack's discussion of the holomorphic index formula probably led to half my work. And of course, so if you take the holomorphic index formula, it's an analytic relation. You can just, algebraic relation, you can differentiate it. It gives you a formal relation. It gives you one condition, one constraint. You might wonder if there's other constraints. Now, if you step back and just remember your complex dynamics, it's very easy to convince yourself there's no other constraints. You can just exhibit maps with multipliers. But the spirit here is to do things infinitesimally in a general setting. So the fact the infinitesimal holomorphic index formula arises from the fact, this is a very, very funny fact. If you just consider the formal expression, and I hope I have this right, so you take any rational map F, and you look at the formal expression f prime of z, I know I'm using coordinates, but I sort of have to for this, f prime of z divided by the difference z minus f of z, squaring that. Normally you wouldn't square it, but you've taken the derivative, so we get square in the denominator, get the f prime on top, and just, it's supposed to be a quadratic differential, you just trust me. So slap on a dz squared. And miraculously enough, despite how it looks, right, that expression is coordinate covariant in the sense that if you conjugated the f by a Mobius transformation and then followed the recipe for the new map, so of course that conjugation wreaks havoc with the subtraction. And typically you'd think that this would mess you up and you'd only get agreement up to some correction, but it actually works on the nose. It's a neat fact. Okay, so the fact that that thing that you write down has these properties is the infinitesimal holomorphic index formula and gives you your constraint, and then some dimension count with the residue theorem, things properly organized, gives you this statement here that subject to that relation there are no others. So now I'm back to indices, right? So if I were working with multipliers, it was somehow much messier. So the correct move was to go from multipliers to indices, and this automatically recovered the parabolic cases. Okay, so of course I'm going to have fewer than d plus 1 fixed points if I have multiple fixed points. However many fixed points I have, one less than that is the number of independent local analytic coordinates we get from this. And of course, if one's wondering what I mean by local, because we don't have the inverse function theorem in the algebraic and in the Zariski context, you could work in the 8-column context, for example.
I didn't quite
Understand what
understand.
the formula means.
Which formula?
When you say that this is zero,
Oh.
one-dimensional.
Oh, okay, fine. Okay, it's because I did not prepare a slide on how to compute H1 via repetitions. So this is a repetition. Okay, here, this is, you can see I'm looking at the set of all fixed points of f. For each such fixed point, I look at that expression. I really look at the polar part of that expression. So that thing with a bracket means take the polar part at the fixed point, starting with simple poles. Later on, the polar part will mean something slightly different, but here it means starting with simple poles. I do that over all the fixed points, I add them up, okay, and then an object such a sum of polar parts automatically gives you an element, or can be interpreted via the Adele repetition presentation of cohomology. That gives you an element of H1 in that twisted sheaf. This is quadratic differentials requiring zeros, imposing zeros appropriately along critical ramification divisor. Now you're not going to get any global ones, right? Because you need poles first of all, right? But you will have first cohomology, okay? And this gives you, so an expression of this kind would give you always an element of that first cohomology. And I'm claiming that this one always gives you zero. That's the holomorphic index formula. This one always gives you zero. The proof, what's the proof? The proof is exact, here's the proof. The proof is that they're all restrictions of the same global. The proof is remove the brackets. There is a global object there, right? And by the definition of H1 via repetitions, it follows that it's zero. That's the proof.
What is this H1 by something? What is this H1 by something whose name I didn't mention?
Adele's. Repetition or Adele's.
Can I suggest a way of understanding that?
Please,
You have
please do.
some things defined on a bunch of open sets, and then you take your differences on the overlaps. Okay, I just wanted.
Hello? I just wanted to translate from Adam to a different language, which is that if you think of cohomology in terms of coverings by open sets and things defined on differences of coverings, if you have a bunch of objects defined on the individual open sets of a covering, then you can take the differences in their values on every pair of intersections, and that automatically is an element in H1.
Yes.
And so you go from, so to speak, chains to the boundary of chains, and that's this map to H1.
Which is what it is. It's just that account doesn't necessarily explain what I mean by that notation. I mean, my notation really still is using repetition.
Explain what you're doing.
Explains what I'm doing. So let me just say one more. So I didn't say what the dada. You allow yourself at every point in P1, you allow yourself to write down a polar part. Okay, except you only allow yourself to write down non-trivial polar parts at finitely many points, and then you mod out by what would happen if you had only trivial polar parts everywhere, or the system of polar parts for any global object. Okay, and because if you remove the brackets here, it's the same formula. That's a global object, and therefore, as a repetition, it's trivial. And
What is the word repetition?
repetition. I thought that's what it was called. I thought that's what they called it, or that's what they and Sarah call it. It's essentially a DELS, but a DELS involve an extra completion, which is gratuitous in this case. So formally it's a restricted product. Okay. All right. So now, I mean, at this point, I have to start waving my hands because the computation. I'm sort of suppressing some of the computations, but actually, in a way, I'm not, because many of the computations that one might think one might go about doing happen automatically by virtue of the formalism of cohomology. I mean, for example, the fact that you embed a discussion into cohomology may well already take care of checking that certain things you worry about are well defined. And as a bonus, phrasing everything in terms of cohomology plugs you in. It's like hooking up to the internet. It plugs you into the larger world of other subjects that are also written in the language of cohomology, like algebraic topology, class field theory, etc. Right? So not that I have any connections I can make here, but maybe someone else can via the formalism, because there's somehow only one cohomology from these characterizations. Okay, anyway, so here it's going to go a little bit fast. This is sort of for the experts, but this is all tautologies here. So if I look at this, what does this upper row here mean with exact sequences here? Right, so I can look at the sheaf as an exact sequence of sheaves. But you want to think of this sort of pointwise or locally. So you have, look, I have a vector field. I can be talking about holomorphic vector fields, or I can be talking about holomorphic vector fields required to be 0 for various orders in various places. Or I can look at the quotient of vector fields, holomorphic vector fields by that, right? And I can do it along a set B or along a set A, and be reasonably arbitrary. But if I want to have a diagram between them, where the diagram is something that I don't have to write down, it just rains down from the theory, then you need this condition here. The fact that the cardinality of A is greater than or equal to 3 is for something on the next page, the usual meaning, right? But I mean, these conditions came up, for example, in Sarah's talk. They're coming up for the same reason here, but here we first see them in terms of what does it take to get this what does it take to be able to legitimately write this diagram down? Okay, and essentially, I mean, the existence of these vertical arrows is all due to the fact that we know how the orders of vector fields are supposed to behave when we pull them back, when we might acquire, what happens if we start with a 0, when we might acquire a pole, and so on and so forth. And so, if I really want to take this at face value without worrying and checking about everything, then I'm going to want to assume tame ramification, I think. There's probably a version of this diagram, the next diagram, for wild ramification, but it may not be the version I've written down because remember that thing with the inequality there. So I'm not going to go there since it's tame ramification, or it's characteristic 0, or it's C. Okay, but there will be no analysis. Okay, so what is cohomology? Cohomology is the unique thing up to unique isomorphism, which turns short exact sequences into long exact sequences, full stop. So that doesn't need a proof, it's really the definition. All right, and then, okay. Because the things I'm talking about really are best phrased in terms of cotangent vectors, I'm going to be dualizing things the way it's called Serre duality. There's a relation between, it turns out there's essentially, if you're talking about sections of sheaves associated with line bundles, then H0, the dual of, you're wondering what is H1, sort of abstract, but H1 for a line bundle is canonically dual to H0 in something related to that line bundle. You take the dual line bundle and you tensor with the cotangent bundle, and that's Serre duality. That's what it is for sections of line bundles. It behaves a little differently with the skyscraper sheaves. I'll discuss that with people after the talk. I just want to write my diagram. So you take this diagram, you dualize, you think a little bit about what's supposed to happen at the co-kernel, at the skyscraper bit. You get this diagram. Now, this diagram, in fact, we're at this point, in the spirit of JackFest, spirit of my previous JackFest talk, right? I mean, this diagram appeared in that. This is one of the diagrams that appears in my transversality discussion, although this is not really, this is the one that relates, this is the one that's there, so to allow you to transfer transversality computations done in the deformation space, where somehow things are more transparent, to the results that you probably really want, which are things happening in parameter space or moduli space. Okay, so anyway, just to sort of walk through this diagram here. So this diagram just presents itself when you make those formal moves. The thing I've labeled up there with T star relative depth, that's not what the theory tells. The theory tells you there's a co-kernel there and that there's a kernel here, but we've already identified those. Well, we already identified this one in the previous slide, and well, basically that one is in my thesis, right? But I mean, any of these discussions with the deformation space are predicated on the fact that the cotangent space, the deformation space, is by definition, or by isomorphism, the H0, so holomorphic quadratic, so meromorphic quadratic differentials allowing simple poles in D, modulo the image of identity minus f pushed forward, acting on holomorphic quadratic differentials allowing simple poles in A, and you have that co-kernel. Okay, now, the experts who were asking about lattice examples and this is where that would happen. So if you look at this diagram over here, everything on this side of the diagram in particular, this column over here is where where that discussion of fixed point multipliers was happening. I said it was quite easy. Whereas over here, when people are interested in, for example, computing variational formulas for multipliers of cycles or holomorphic indices, or discussions of parabolic degeneracy, as in Xavier's talk, and they're probably they may be writing things down in terms of Beltrami differentials because they'll get deformations. Whether it's realized or not, those computations are happening in the deformation space, or tangents to deformation space. Okay, and that is where we know how to give criteria and arguments for transversality of things like critical relations and higher period multipliers. And those things all rely on Thurston rigidity or certain amplifications of that. So any statement to the effect, for example, that this operator here is injected. So I could, if we decided we could label a kernel here, and if I put a 0 in there, that's using infinitesimal Thurston rigidity. Okay, so people are also probably more used to the presentation of this in the analytic context, where the tangent space to depth, the dual of this, right, is perhaps expressed in terms of Beltrami differentials rather than first cohomology in sheaf of vector fields of zeros. But again, because there's only one cohomology, right? So there's something called the Dolbeau isomorphism, which will enable you to show that writing things down with Beltrami forms also computes cohomology. Okay, so if you like Beltrami forms, if you like analysis, you can do it that way, which is safe if you're overseas, but you don't have to. You can phrase it cohomologically and make sense of it much of the time over other fields and all of the time over Q bar. It's just that to prove that this is 0, this is the place, and the only place in my discussion where I would ever be using C. And of course, my secret agenda for the rest of my life is to try to get rid of that. Which dynamical state? No, there won't be any. The talk is about the formalism. That's what the abstract said. The talk is about the formalism. Now,
just illustrate how formalism goes.
So okay, here, I can do it right now. Okay? No, please let me do it. It's my talk. Let A take a post-critical finite map and let A equal B equal the post-critical set. Okay? Okay. To claim that map is an isomorphism, that's Thurston rigidity. It's infinitesimal Thurston rigidity. This arrow here, to say that this arrow here from that to that is an isomorphism, this would be H0, this would be quadratic differentials allowing simple poles along the post-critical set, same space there. To say that identity minus F pushed forward is an isomorphism is the infinitesimal step in Thurston rigidity, and that you see.
And
yes.
And it is to say there's no quadratic differential, which is equal to a push forward.
Well, yeah, that's okay. That's what I call infinitesimal Thurston rigidity. I don't know if that counts as a dynamical statement, though. I don't know what the rules are. So,
well, you have this thing delta F. I'm just
now
rephrasing what you just said.
Yeah.
Delta F.
Right. No, I mean in terms of Misha's question. So, okay. Oh, I should say at this point, all the pretty diagrams, like for example, you notice there's some shading here. It's maybe not so visible from the back, but that will be helpful later on. There's a slight pink shading there. Any of these color diagrams, these are made by Xavier, and some of them are quite impressive. So, yeah, okay. So this is the exact sequence which is containing the relation between the infinitesimal deformation space and the infinitesimal moduli space. Really on the whatever. Okay, now, here's another one. Actually, this exact sequence was played with even earlier. This is the one that's used in like the Tushkura paper. So here, now, this is a little bit important. So now I'm going to be allowing, okay, so on the vector field side, it's mandating higher order zeros, but once I go by duality, it's going to be allowing appropriate higher order poles, higher meaning 2 or more. So this is best expressed in language of divisors. Think of this as a multi-set. So we already have sets A and B satisfying those previous conditions. B contains A, f of A, and a set of critical values, and A has these 3 points. And now suppose that you take those sets and you just add in higher multiplicities at some of those points as you like. Okay? I mean, keep everything fine, up to some multiplicity, say. Okay, and then do the same thing for B, or do a compatible thing for B. And then again, without actually having to do anything, the theory gives you, again, why? Because of the, well, look, so what is this upper relation to? This upper relation says, look, if germs of vector fields requiring zeros of a high multiplicity, okay, that'll inject into germs of vector fields requiring only zeros of multiplicity 1, and then there's a quotient. And you can do it for the B, and you can do it for the A, and the existence of these downward arrows follows tautologically from the relations between the A's and B's mandated before, okay? And was there a snake? Oh, I think.
What's this?
The previous, there's supposed to be, the point is I think this slide is supposed to come in after this one. This snake, okay, skip this one. We have this diagram here, and when you have a diagram of this type, you can apply the snake lemma, right? You've got the kernels on top, you got the kernels on the bottom here. I've suppressed these because I don't care about them, okay? But really, it's going to be 0 goes to the kernel of this, goes to the kernel of this, goes to this kernel, which goes by the connecting homomorphism to that co-kernel, which would then go to the next co-kernel and the next co-kernel, but this is really all I care about. So again, the interesting part, I mean, this is all tautological, but the tautological part that's at least interesting is coming up from this connecting homomorphism. And so in other words, the transfer from the cotangent space, the quote cotangent space of moduli space, to the cotangent space of deformation space, comes from the connecting homomorphism. Now, by the way, why is this cotangent space of the deformation space honest? Well, I mean, at this point, let's say if I'm working over C, remember this is Thurston rigidity. If A is equal to B, it's Thurston rigidity. If B is bigger than A, it's a transversality statement. So, in other words, the statement that the deformation space is smooth, right, is reduced in the sense of the word I had in the earlier slide. That is implicit in that notation there. Otherwise, you'd have to be talking around that the way we're talking around it for RAT, and I'm not sure I can because I have a nice example, if there's time at the very end, where that space is absolutely reduced for obvious reasons. All right, now, this slide should come after, and so here, this presents a different diagram, shaded in a different way. This is the relation. Now, this is what I use in my proof of the bound of non-repelling cycles in terms of the number of post-critical tails. So this D of FA, this is the kernel of the arrow going on top. This is what I call the space of invariant divergences. D for divergence supported on the set A. Now what is that? Okay, or a subset of it, because I haven't necessarily allowed poles of arbitrary high order because I want things finite, but whatever, up to whatever order I care about. So what is that? So a divergence by definition is it's a class of polar parts, but for the purpose of this discussion, polar really means starting at what? At polar order 2. So in other words, it's a collection of polar parts starting with double and worst poles. Simple poles count as non-singular for the purpose of that definition. Yeah, yes, I know, and I hope you know that. So, and there's a natural notion of what it means to be invariant. It's basically the ones that come out as that kernel. These can be classified. They're completely classified into local data in my paper that's been on the archive for ages. In fact, this connecting homomorphism here, right? So, if you could show that the connecting homomorphism is injective, or if you can show on a subspace that's injective, that will tell you that the dimension of the subspace is less than or equal to the dimension of the target. And we know the dimension of this, at least if we're, say, in characteristic 0, because Thurston rigidity tells us that the dimension of this is the number of points in B minus A. The number of post-critical tails, if we take A and B large enough, and the space of divergence essentially counts in an explicit way the non-repelling cycles. So, okay, now of course, to get this injective, when you actually prove that theorem, you have to restrict attention to the non-repelling cycles because that's where you can prove injectivity, and you shouldn't expect injectivity anywhere because it's very easy to get an infinite dimensional space of invariant things. Okay, so again, this is where the formalism takes you so far. Right? It doesn't trivialize anything else, but it sort of highlights where the difficult analytic content is that you might want to get around with new mathematics on the arithmetic side. Okay, so now this tour de force through the Xavier is the argument, the final consideration really comes out of putting these things together. So we have one of these diagrams at the bottom. On the bottom we have the diagram that came from the transfer between moduli space, infinitesimal moduli space, and deformation space. And on this side, on the vertical wall, we put in the diagram used to bound the number of non-repelling cycles. And then if you take a look at where the exact sequences these things came from, it's actually there's versions of this, with bold-faced A and so on, and on other levels here, and there's versions of the vertical one. So the whole thing, in fact, is a nice. Okay, so we're still assembling it here. So we're going to get a 3x3x2 diagram. That's the core of it, and there's actually zeros. Everything is somehow coming about in the exact sequence. So there's zeros coming into everything and zeros going out, which will be suppressed in various other slides. Although that zero is essential there. Okay, so this is what the front 3x3 thing looks like, and then on the back, it's basically the same thing, except the B's have turned into A's. Here's Xavier's beautiful picture. The shading is probably not as bright on this projector as it is on my computer. It's all here. You even got all the labels right last night. And so what are you doing of a diagram? Then we already know what you do. You get it with the snake lemma. There's two snakes, and there they are. Right, one snake is going from the invariant divergences to the cotangent space. That's my Fatouche-Shgur description. And the other one is going from the tangent space to moduli space to the tangent space to deformation space, which is how you transfer results. By the way, again, that's not always an isomorphism either. That you can show that this is an isomorphism when something here has no kernel, and that's precisely when you haven't marked any cycles of multiplier 1. And this came up in Xavier's talk. He mentioned he had to do a workaround for that. Okay, so look, here's the thing. I'm just arguing, I'm going to summarize. I'll tell you what it proves at the very end. At this point, we've got a diagram. We're just playing with a diagram. Now, in a general 3x3x2 thing here, you're not going to be able to you're not going to have any relation between this lower pointer and that one. But notice there's zeros up there. The fact that these two are zeros, in other words, the fact that these are isomorphisms. In fact, they're probably the identity. Yes, they are the identity, right? So those quotients are trivial, but that imposes that puts serious constraints on what's going on here, because of course there are also zeros from this direction here. So actually, okay. So because of that, it follows, in fact, that yeah, I'm finished. Because of that, it follows that where is it? This arrow, which in generality only goes this way, here for the same reason. And you can do that in the front face, and you can do it in the back face, and the whole diagram commutes. Things are exact, the whole diagram commutes, so therefore you can do it for the kernels in front and for the co-kernels in back. So we've done it here for the kernels in front. If you take the kernel going in here, then you have a tautological map down there, a tautological map up there, and it looks like your first thought might be, wow, now we've got a commutative square. But when you sit down and compute it, it's not going to be commutative. It's close to it, but not, and that's somehow a point, okay? Because I'm really finishing here. I just need to show the last slide, and I'm finishing here. Can we get this back up? And I will finish. I really will finish within 2 minutes if I get that up. No, I'm not kidding. There's no point having gone this far without. Okay, so, but this is not working anymore. Okay, so next diagram. Can I hit return? Okay, now this has been extracted. The whole purpose of the rest of the diagram, at this point we're looking at the part of the diagram we want. So this is the kernel going into the middle bit. These are these two snakes. The green arrows are what we get because we had zeros up there. The n doesn't belong here. I'm not claiming this is a commutative diagram, although you might think it is. In fact, when you actually think about where it comes from, there is a tautological map for the rest of the diagram from K down to here, and it's actually 0. And that, plus the fact that all of these ruminations here imply, business of the zeros in the quarter imply that the kernel is canonically direct sum of the two corner bits, and the fact that the conjugate from the kernel down to where you want to go is 0, basically tells you, and Xavier had this in his talk, our version of it, where he basically said there's a residue theorem computation where you want to compute something for the cycles, you trade it for a certain computation for the critical points, and a minus sign comes up, and that's what it is. Okay, now that's the derivation of something. You might wonder what this is. For example, you can use this. Once you have this here, you can interpret this. A special case of this is the variation of formula for multipliers. So purely algebraic derivation that's valid. I think probably valid for tame maps of any characteristic in any characteristic. Certainly no complex analysis. Okay, so this is essentially the end of my talk. There's one more slide. Who's operating it? Did I just hit return? Spacebar. So happy birthday, Jack.
Thank you very much. Please, for questions and comments, please conversate Adam personally. Thank you very much.
Okay, so